music making software on Linux is so genuinely dog shit that I consider.
I think they're able to crack tables on Linux. They don't run on Linux.
Okay. Yeah, FL Studio is the one I really like.
LMS
is great for the panel, but
it doesn't have great other integrations.
and there's no plugins. It bundles with some great plugins, but it has no.
It doesn't have music. Nice.
Yeah.
It's like, how PHP3 is old? It's not new. Wasn't there a new? Wasn't there a new one that's supposed to be like open source and everywhere now?
I think so.
The problem is the music industry is going to take forever to adopt that if it does ever.
Yeah, last night I was trying to figure out like what the baselines. I just wanted to find like a keyboard audio. I think I could get it to make it without making a big dollar like any crazy overhead. I just wanted to make it.
All right, students. Hello, it's me. I have my wallet and nothing else. I don't know where my phone is. I have one key, but not the rest of my keys.
I was using it over. You guys probably be the case, I think.
Probably not. I feel like I know if I got robbed. I have my wallet. That's the first thing you take, right?
So maybe that's just you get mugged?
Yeah.
I don't think so. But see, right, like memory's an imperfect storage medium, right? So like maybe I mallocked it, right?
Right.
And maybe I didn't finish writing malloc, so I just don't remember getting mugged. There's lots of things I should do.
I'm sure I think there's code in there that that makes that pretty high priority. So I don't think that one would have failed.
You would think that, but I fail at lots of things.
Right.
Speaking of me failing at things, how was... Okay, sorry, I have to be more specific, because I was going to say the coolest assignment of all time, but both of the last two assignments I have described that way. How is the one where you have to use QEMU?
I have not started. It's very easy. Am I getting shit?
Okay. So it's easy. Okay, cool. Here, I'll say this out loud. I know students love it when I do this. I'm glad you all love it, right? Okay, cool. So today, we're going to talk about kernels. So some of you who know fear, notice there's a 90 down here. I started, this is the second week in a row where I'm like, this looks easy. I should just explain the few parts that are confusing. And then after like 8 hours of making slides, I'm like, we're probably not going to finish this.
It's all confusing.
So, well, I don't think any of it's confusing, but some of it's really cool. So also, this citation is wrong, because I claimed I just actually compiled this thing directly into slides. That's not true. I rewrote the entire thing. Background. Okay. So everyone likes POV, right? Right? Like my face when I'm an inanimate piece of silicon, right? So you're hanging out with your friends, right? You got maybe some registers, right? And what's a register? It's an ordered collection of bits, usually of a power of 2 length. And there's probably some wires connecting your registers to each other, right? Does this sound fun? Does this sound like what you do with your friends, right? And maybe you got like 1 trillion of them or something, right? Like a lot. Like you're probably not keeping track of all of them. But here's something I haven't pointed out, right? I haven't said you have any electrons, right? Like maybe you're fresh out of electrons. Maybe you alone, of all of the atoms in the universe, have exactly 0 electrons, right? Perhaps you're a hydrogen ion or something, right? So you're hanging out with your friends, right? And you got all these wires and you got all these registers, but they don't have any bits in them, right? Because there's no power, right? Not to worry. Somewhere, I'm thinking about Frankenstein a lot because in my last class I just talked about Frankenstein for 90 minutes. So somewhere, someone throws a switch. And is that person Victor Frankenstein? We can't possibly say, right? But so maybe somewhere a switch is flipped. And then all of a sudden the electrons show up, right? You're like, oh, cool, electrons. This is exactly what I was hoping to push through my wires and store in my registers, right? But how do you decide, you inanimate piece of silicon? Remember, you have no feelings or thoughts or desires, right? You're simply behaving deterministically according to naturalistic processes where all of your electrons go, right? So you've got these, perhaps some logic gates, right? Are you all familiar with NAND, not AND. Yeah, that's one of the logic gates. We got XOR. Any fans of XOR? There's some other ones too. Yeah, and so you got some logic gates. And where do the electrons come from? Do they start in every wire at the same time, or do they perhaps come from one wire? I always get my electrons, so I have ethically sourced electrons. I get mine from hydroelectric dams in the Pacific Northwest. And the only thing those hurt are salmon. And if there's any people that have relied on salmon, it would hurt them too. But I didn't learn about them in the American public school system, so that's probably fine. So I have my ethically sourced electrons, and they're passing through my wires, but not all of my wires at the same time. Specifically, they start at the place where the electrons come out of the wall and then go into my computer, usually through a power supply. And so, folks, what we have to deal with here is we have to deal with a little thing called the boot process. So you know how when you first get up out of bed in the morning, the first thing you do is put on your boots? That's the exact same thing that computers do, right? They're just like us for real. So there's this thing called the boot process, and it only happens once for some value of once, right? Unlike me, if a computer dies, it can be turned back on again. I lack this talent. So this does, in fact, happen more than once to computers. But since this is in my... what does POV stand for? Point of view. So from my point of view, once I run out of electrons, I no longer suffer. Okay. So every power-up, every time Victor Frankenstein flips the switch on the wall, the same electrons flow to the same space. Does this say ever power-up? No, that says every power-up. There's an invisible Y. You just can't see it, right? And this stuff all happens before there's any operating of any systems, right? No one's operating the system right now. The system just is. It is behaving according to exclusively naturalistic processes. So I'm going to introduce a term, and some of you will have heard this term before, and some of you probably haven't. I don't know. It's firmware. And the geniuses that cooked up this term, this is so elite. What's between hardware and software, right? See, so I always said wetware, right? So like I run on wetware because like I'm squishy and fluid. I think wetware is like a real thing. Should I type this in front of class? It's going to be weird. Wetware film.
This is like the worst time possible for Cassie to be gone.
Why? That's why we can look it up. We don't want.
We've ever had discussions with her about it, but definitely a fan.
Yeah, so that's what we waited for Cassie to leave. We brought up wetware. Now we're going to close the window. Okay, everyone act natural. Okay, right. So firmware. Firmware, I think, matters. Do you all look for jobs ever, or are you just going to graduate and then realize you don't have a job yet and then panic and blame me? I kind of feel like it's going to be the latter one. Wait, why are we looking in Salem? Hold on.
Firmware jobs in Salem.
There's firmware jobs everywhere. Okay, there. Wait, why doesn't it say the number? Oh, there's a bunch. So why might I, someone who has trust issues about my students actually getting employed when they graduate, no matter how well I prepare them for the workforce, be bringing up firmware in class? No one could possibly speculate. Oh, look, it's a summer-fall co-op in Hillsborough at $42 an hour. All you need to know is Python, and I will say you have a master's degree in your letter of recommendation. That's fine. I'll lie. That's no problem. Let's see. Do you know all of these things? You know C programming for embedded systems. That's what we're doing. You know Python scripting for automation tasks. You know embedded development environments. Kind of looks like you can do this. Do you know any of these things? Oh, version control. We got that one. Do any of you have strong problem solving and communication skills?
Yes, we all have that.
You all have that, and I will say you have it in your letter of recommendation. Okay? Don't mess with me on this. I know you have it, okay? Just because I've never seen you use it in class doesn't mean I won't testify in court. Okay. I wonder if there's anything else in here. Oh, everyone wants to work for Intel, right? Do you see these salary numbers, by the way? Are you looking at these salary numbers? That says 128, 880 to... Okay. Do you have any experience in software coding? I bet we can do that. Okay. C++ and Python? I've probably taught you C++. Have I not?
No, I forgot.
That's crazy. Jimmy keeps just like posting random things that only make sense if you know C++ in different places in Discord, and I'm like, Jimmy, you have to teach them C++ before you can do that. And Jimmy's like, but
You don't have to know C++. The code was all in Rust.
the code was all in Rust. And what was it doing in Rust, Jimmy?
Interrupting the C++.
It was interrupting with C++, right? Okay, so anyways, firmware. My first job in the tech industry, I designed firmware for hard disk drives. It was a great time. They were going to invite me back the next summer. This was 2012. In 2013, Samsung decided that hard disk drives didn't exist anymore, and they were completely correct. So that industry was gone in 9 months. You know what's not gone? C89, still around. Okay, so all the stuff I'm teaching you should be durable, especially your communication skills and your problem-solving skills, okay? You notice how like on Wednesdays I have labs where you all work together on a hard problem together? You all notice that? Okay, all right. Okay, so we got this stuff called firmware. What makes it firm? It's harder to change and update than other software. So usually this is something that looks an awful lot like software, but maybe it lives in a specific memory or a specific location on your device. Perhaps it cannot be set after by anyone other than the manufacturer, but it is in fact set by the manufacturer after the device is created. All right? And so here's what we're going to claim. On power up, when I start pouring my electrons over your head, or no, when Victor Frankenstein starts pouring electrons over my head, there we go, that's the metaphor. Devices execute code embedded in a physical read-only memory, which we also call ROM. Were any of you around when people were still calling CDs CD-ROMs?
Not around, but like I've seen that. For
Yeah. Yeah, right. So the term CD-ROM, and why is that? It's because the competing technology was the CDR, where you have a never mind. There's other things. So the CD read-only memory comes off disks. It's much less common to have ROM around now, but it is very, very important for getting the computers to turn on at all, so that's why we do it. Is firmware software, is it hardware? I don't know, right? So when I first was doing firmware, I was like, this feels an awful lot like writing code, the thing I do to make software, right? But now sometimes I write code to make hardware too, so the writing code for it to be software is like, that was fake the whole time. Okay. Oh my gosh, it's a reference to Alien 1979 in one of my lectures. How do we fit that in? That's wild, we fit that in. Okay, so usually power-up occurs on something called a motherboard. I don't know a ton about motherboards, but for a while, Asus was making really highly regarded ones. And the Taiwanese Semiconductor Manufacturing Corporation, which is the only company in the world that matters, they get all of their employees Asus laptops for some reason. I used to have an Asus. I stopped using it because the D key broke. And
going right a lot in video games.
yeah, because I only go forward in my platformers. Yeah, I was playing Hollow Knight on my work computer on a 14-inch screen in between classes. No, the only thing I do in my office is eat sandwiches. That's why I close the door. None of you are allowed to see me eat the sandwich. You can always knock, and I'll put the sandwich away and then talk to you, right? But you're not allowed to see me while I'm eating the sandwich, okay? I'm like covered from head to toe in peanut butter. It's disgusting. I'm very slippery. Yes, I can fit in very tight places. Yeah, so the motherboard is named after Mother. That's how it's pronounced. That's how they say it in the movie. I would know. I've watched that movie enough times to check. But I only watched it because it was my job, okay? So, Mother, which I had no idea was spelled that way until I looked at the script. That is a sick way to spell mother, right? Like, shout out moms, right? What a killer name. So Mother is the on-chip computer in Alien, and it's the namesake of the motherboard, right? Moving on. So, firmware... We're not going to write firmware this term. Or ever. There's no planned future in which we write firmware. You can write firmware. It's not that hard. It's just bare metal stuff. Is it just like bare metal stuff? Oftentimes you care about things like a very specific memory address, right? So it isn't really like CPU code. When I wrote firmware, I actually didn't write it in C. I wrote it in this language called Forth. Have I told you all about Forth?
Oh, you wrote Forth?
Yeah, I wrote Forth.
Fascinating language.
This is why I care a lot about stacks, because I spent my summer thinking about stacks before Samsung forced me to go to grad school. Wait, how do we? I'm saying Samsung. It's got to be Samsung, right? How do you? Well, we've always said Samsung, but aren't like at least one of us is a white person from the suburbs. Well, I looked this up, but that doesn't actually help because I don't know what any of these symbols mean.
IPA?
Wait, what? I don't know the IPA. The only IPA I recognize is the India Pale Ale because I'm from Portland, Oregon. Okay. Okay.
Right here.
Here, I'll embigify it. Well, actually, wait, I don't know how to do that on this computer. There we go. It's.
Are you sure you read IPA?
I read French and German.
Oh, this is neither French nor German.
Yeah.
Okay, I'm just gonna
It
say
should be Samsung.
Okay.
we think it's Samsung.
Yes.
Samsung. Hard U.
There's like
Song.
not a strong G, but like it's the.
It's aspirated.
It's the
Samsung.
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 Okay.
This is not remotely relevant.
I think
So it's like an S, except there's more breath.
it's important to get the names of like the Korean companies correct.
I should ask my uncle.
Yeah. I like have this low grade annoyance that there's like extreme Anglocentrism in computer science, and I don't really want to be contributing to that. And it's not my fault that I didn't even know Alonzo Church was American, which is the only thing worse than British you can be, when I decided to make my entire personality liking Alonzo Church's lambda calculus, right? I assumed that someone named Alonzo was Italian or something cool, like Irish. I don't know. Anyways, so okay, so you got your CPU code, or it's not CPU code. It's not even remotely CPU code. It's motherboard code, and motherboards don't like execute code blocks. They just like turn on an LED or something. So I will return to my favorite running example, thermostat. The thermostat, you don't use it to calculate things, right? It just does stuff, right? And it doesn't do particularly sophisticated things. The only responsibility of the motherboard is to turn on the CPU. So the motherboard looks at all these electrons and they're like, oh, my friend CPU, which stands for the Kelvin processing unit, asked for these electrons to be put into these 4 wires at this fixed rate. And you're like, okay, cool, thank you. The motherboard, of course, does not only turn on the CPU, it also turns on the MMU and whatever else you're going on. And so now we recall that the motherboard is awfully close to being a smart version of the bus. So it's the bus with a little bit of brains in it, right? Bus comes on first, wakes up the CPU and the GPU. And that's not literally what happens, but that's a close enough metaphor. So we knock on our CPU's door. We sort of go into the CPU's. How do you wake things up? You take the cat off the CPU's bed, and then okay. So you wake up your CPU, and every clock cycle, which is some fixed amount of time, so every nanosecond, you dump a new bucket of electrons on top of the CPU, right? And so then the CPU gets all loosey-goosey, gets all warmed up, gets all ready, resets itself, and then the first thing the CPU is going to ask for is like, well, I'm a central processing unit. I need something to process. And you must immediately furnish the CPU with one of 2 things, a bare metal executable or an operating system. So the operating system will persist and keep going. And the bare metal executable, operating system is a subset of bare metal executable, right? But you could have a terminating bare metal executable, right? You could perform some big calculation, write the number in memory, and then go back to sleep. That's completely legal. That's totally allowed. So motherboard, power flows through the motherboard. Motherboard takes the power, directs it through the CPU in a specific manner. The CPU wakes up and comes alive and starts looking for the first code, right? There can't be anything in between that. Okay, so I feel like no one ever told me why operating systems were called operating systems, and now I'm afraid to ask, so I'm just going to speculate. I'm pretty sure this is true. I think the operating system is the system that operates the hardware, okay?
Yeah, that makes sense.
and I think it does so on behalf of something, usually software. So I'm not really the person that is interacting with the operating system. Usually I boot up Firefox and use it to go to TikTok. So I'm a client of TikTok. TikTok is using Firefox. Firefox is using the operating system. The operating system is directing the motherboard how to use the network controller and the CPU card and the GPU card to display cat videos on my monitor, right? And so, because we're talking about making a system that operates hardware and not because we're talking about making a video player for TikTok or any other application, that's why we call this systems computing. It's something that is in between the stuff the end user uses and the hardware. Oh, yeah. So there's something called the power on self-test, and the electrical engineers care about it a whole bunch. So please repeat after me. I have heard of the power on self-test.
I've heard of the power on self-test.
Thank you, very good.
What is it?
I gave you a link. It's called the power on self-test. What do you think it is?
I imagine that it has something to do with the power system. Yeah, that.
Yeah, right? Okay. Do you?
Whenever the computer powers on, it tests that all of the components are working.
Okay. Do we know more than we did before we paused to answer that question? Okay, all right. Yeah, so thank you for your answers. And so I also just had an entire slide where I just explained what an operating system is, right? Okay. Okay. Fortunately for us, there is no widely agreed upon way to do firmware. To do firmware, that's a pretty big phrase, so that should be unsurprising. There's not a widely agreed upon way to do that. But I'm gonna tell you right now about two ways. There's the cool old way. It has some problems with it, but it's always worked okay for me, and that's the BIOS. The BIOS is super cool. BIOS has the advantage of being called BIOS, which is like one of the coolest names you can have, right? It runs before the operating system. It has OS in its name. It inexplicably has the same prefix as biology. What? How did that happen? And that's from 1981. For those of you who are following along at home, 1981 is 2 years after Alien came out. It's 1 year after Reagan was elected president, and it's a large number of years ago from today. Does anyone know how many years ago 1981 was?
45.
Good job. Is that true? Yeah, probably. Oh, it's 2026?
Yes.
Cool.
Sorry.
Okay. So, besides the BIOS, which is awesome, there's the new way that is too hard to use for normal people like us. And by normal people like us, I mean I would probably want to teach a whole class on this. So you've noticed there's like been 8 times so far there's something that comes up that I would have to teach a whole class on. Maybe that's because I'm bad at teaching, but anyway, I don't know why. So the way I think of it is, unless this is your job, use the BIOS. If this is your job, definitely don't use the BIOS. So if you get one of those firmware jobs, maybe you're not going to use the BIOS. That said, I think a lot of those firmware jobs are going to be working with Internet of Things stuff that are probably using older standards. Okay? So this new standard is like super cool and good or whatever. It's called the Unified Extensible Firmware Interface. I might make you use it for a lab, but I'm probably not going to because I don't care about it. And it came out in 2006, and for those of you following along at home, that's 2 years after the release of Alien vs. Predator and 1 year before the release of Alien vs. Predator Requiem. So that's between the 5th and 6th films in the anthology, instead of 2 years after the first one. Okay? I can do dates with other things if you want. Okay, who was president in 2006?
Bush.
Which Bush? Yep, the Strategic Bush Reserve, right? They ran out of bushes and they got another one. Okay, who is the Speaker of the House?
I don't know.
Nancy Pelosi. Okay.
Wow.
Yeah.
Most of us were people like,
I was definitely
You don't even know who the Speaker of the House was in 2006?
2006 though.
And you're blaming a baby?
2006.
Oh, wow.
Jimmy, you're a boomer. Did you not know this?
Compared to everyone here, yeah.
So, okay. I'm gonna out, this is how old Jimmy is. Jimmy plays World of Warcraft. Right? Like he's, no,
A little bit, okay?
no, I have an active subscription, but it's not installed. That's how I. Okay. So turns out I actually knew what a BIOS was from my real life lived experience because I was a child before Alien vs. Predator came out, which meant that if I was playing with computers, I had to play with the BIOS. Okay, yeah, I have an exact quote from the blog here, and I guess I believe with this. It's great that it's still around because you can use the same boot logic across all machines from the last century. So this is good because compatibility is good. And then this is bad because then you have to worry about backwards compatibility forever. So it's the double-edged sword of computer. Blog says something that's not true. I don't believe this is true at all. I don't like this. Blog says it's a downside that this means you have to do everything in 16-bit mode. That's completely fake. 16 bits is enough for everything you're doing. Did you not all just write a memory allocator that only needed 8 bits? Right? That was you only needed 8 bits to keep track, right? 8 bits is plenty to do all kinds of stuff. 16 is more than enough. If you need more than 16 bits, you're writing inefficient code. That's what I say. So just figure out how to get things done in 16 bits if you get stuck. We've written a bare metal executable right here. I'll pull one up. I think I have one somewhere. I think I found it. Is there anything I'm doing here that requires more than 16 bits? Right? Now, it so happens that the way that this is implemented, I sort of require more than 16 bits because I'm running it on 64-bit hardware. So to call a function, you need 64 bits to describe the address of the function and so on, right? But there's nothing in here that inherently requires more than 16 bits, right? And so if people that were alive in the Reagan years were able to write an operating system in 16 bits, and they didn't get to watch Teletubbies growing up and have the access to that higher quality human development index, right? You should be able to get things done with 16 bits if you have to, okay? It's also true that I can't count higher than OXFFFF, which is 65,536. I've never counted higher than that. I never will. The highest population city in the universe has fewer than 65,000 people in it, so I will never need more.
65,535, actually.
That is true. I lied. But it is also true that I said I've never counted higher than that. So, maybe it was a strict inequality. Yeah, think about that? Okay, all right. Whew, just barely got out of that one. Okay, the blog impolitely calls the 1980s bootloaders archaic instead of vintage, retro, or foundational. I kind of think the person that wrote this, Rust... So the Rust people, they think they're better than us. Well, we're Rust people now. They think we are better than other people because they're newer, right? You know what else is new? Alien Covenant came out in 2017. Not nearly as good as the original Alien that came out in 1979, right? So things aren't better just because they're newer, right? They're better because they're type safe, okay? And there is nothing type safe about a bootloader from 2007. Okay. Disks, yeah. I mentioned CD-ROMs, right? And then before CD-ROMs, there were floppy disks. If any of you all, some of you have probably seen a floppy disk. I'll find a picture of a floppy disk so we know what they look like. Do you know what they look like?
Yeah, I'd say probably.
Sorry, I typed floopy disk instead. We'll see if we can get it, right? Some of these little critters. They come in different sizes. And so, I don't know if you had this problem the first time you saw a floppy disk. That doesn't look floppy at all to me. That looks rigid.
There is a reason they're called floppy disks, and I don't remember.
It's because the inside is just it's like a sheet of magnetic
it's polymer.
film.
That's
Yeah.
floppy.
And that thing's...
It's like kind of floppy.
All floppy disks.
It's turbo floppy.
If you let it flop, that's bad.
So all you have to do is crack open this little box here, and then there's something that flops inside of it, right?
It's not allowed to flop.
No, it's not permitted to flop.
So it should be called not allowed to flop.
I wonder if there's a technical name for them. They should just put a logical knot on the floppy.
But it is floppy. You just shouldn't let it flop.
It might actually be... I think they're just called floppy disks, and it doesn't matter if they're floppy or not. It's like a proper noun. It's like if I named my cat Floppy, she would still be the same cat, right? Here's another fun thing about the floppy disk. Oh, here's one removed from the housing. So this is what they look like. So this thing's floppy. Since the way these things work is you rotate them, so you spin them really fast, so there's really strong... Okay, I'm going to say a physics term, and don't judge me if I use the wrong one. Centripetal force.
I like centrifugal, but they're both respected.
I don't think they're both respected.
They're different.
I don't think it's actually true.
This here's centripetal force.
Centrifugal is respected. I don't.
Well,
think
then I'm
centrifugal
right.
is.
Centripetal. Oh, okay, we're completely. We don't need to look at that right now. Okay, you all tricked me. That doesn't matter. I think it does matter that I mentioned floppy disks. Okay, so one of the places that you could boot your device from, especially in the 80s, is you could shove a floppy disk inside your physical computer. The motherboard turns on, hands a bunch of electrons to the CPU, and the first thing the CPU says is, "Bus, I need you to fetch me the outermost bits from your finest floppy disk drive and feed them to me precisely in order." And those bits will, of course, be the MS-DOS operating system, which is the only operating system that anyone used in the 80s. No one used Solaris. Okay. Nowadays, we're cool. We all boot from solid-state drives because Samsung destroyed Western Digital and Seagate. And if you happen to find a device that existed in 2011, it will still have a hard drive in it. Have any of you ever seen a hard drive? Okay. Those are physically around, right? And those have basically... Why is it called a hard drive? It's just a magnet. It's a round magnet, but it doesn't bend. And its rigidity means it can spin very fast. The ones I was working with spun at 72,000 RPM. And it's weird to do RPM because you usually think about it in terms of seconds. So you just divide that by 60 and tells you how much it goes down. But wicked fast, really fast, not even close to as fast as a solid-state drive. Some of you have probably, at some point in your life, booted from USB. I usually boot from USB my devices once in their life cycle, which is when I put Linux on them. Usually when removing I'm so funny. Okay. Olden computers could boot from floppy disks. Okay. Okay. I mentioned 1980s bootloaders. Okay, right. Okay, a bootloader. Okay, so what's a bootloader? One of the great things about the 1980s is they were still describing things as what they were. Like, I already forgot what UEFI stands for, but I know exactly what the BIOS stands for. That's the basic input-output system, right? So we've got a 1980s bootloader, and the 1980s bootloader is allocated 512 bytes. 512 bytes of storage is not a lot, even in 16-bit mode. So why is that? So, okay, so I'm in 16-bit mode. That means my instructions are 16 bits in length, which means those 512 bytes, that's only 128 instructions. So that's not a lot of information, I can say. I also thought it was 512 bits, not bytes, but I could have completely made that up. So what is this? There's a little piece of executable code stored wherever the bootable disk begins. Now, I don't know how things other than hard drives work because I haven't worked with them. But on hard drives, you just go to the outermost bits, so at the end of your rotating platter. And why do you go out there? Because you have the fastest read-write speed at the end because you're rotating. You're rotating at a fixed revolution, so you can read more bits per second on the outside. So that's where you write the OS, because you're expecting to be coring it the most times. Okay, so somewhere around the edge, there's a line that says start over again. And immediately after that line, whichever way you're rotating, begins the 512 bytes. That is the bootloader. And what does that do? It basically doesn't do anything. Pretty much the only thing it's going to say is go to this address. And at that address, the operating system will be written. So you can regard, and this might be sketchy, you can regard the bootloaders, for instance, some like address 0 or something. That might be a little difficult. I'm talking about hard drives because that's what I know. But you should be thinking about solid-state drives, which means you should be thinking about Samsung, SK Hynix, which are the two, they're both incidentally Korean, but they're the high-performance silicon manufacturers that make mostly high-bandwidth memories for data center GPU computation. Only they can make them. Micron can't make them. But Micron is an extremely high-profile semiconductor manufacturer that's based in the United States. They're the United States' only memory manufacturer. They might be the only memory manufacturer other than the Korean, too. And they are based in Boise. Let's just pop open Indeed here. Okay, so if we look for jobs in Boise, do you all know how to do this? You can look for firmware jobs in Boise. Show me a salary. $136,000 to $200,000 a year. Oh, that's a manager. You can't do that. Okay. $80,000 to $165,000 a year. Okay. Is Micron on here? Yeah, let's do this one. Oh, yeah, 260. Did you see that? Okay. For memory, too, DRAM. Staff, product applications engineer. That doesn't look that hard. I bet we can do this. 5 to 7 years experience in DRAM product. Okay, you probably have that. Wait, Python, Linux, yeah? Strong analytical and problem-solving skills. Do you all have that? Excellent communication skills. Okay. Master's degree in electrical engineering, computer engineering related field. We can get you one of those. Hit me up. Okay. So, I don't know. Oh, look, another one. What are these? Field applications. Yeah. So, okay. All right. Sorry. Please get a job when you graduate. Okay. I got an email from one of my former students that's like, hey, I finally got a job. That person graduated like last year. I don't know what they were doing, and that person is not as good at video games as you would expect. So that's 2 downsides. Now, if you're really good at video games and you don't get a job, I will withhold judgment, okay? But I need to see you like on Twitch. Like I need to just open Twitch and you be there. I don't need to have to look for you. Okay. Okay. Who loves data structures?
Yeah.
Wow, that was kind of crazy. I was just thinking about key value storage the other day. I referred to bin packing, or like I used bin packing to describe something in a CS faculty department meeting, and I seem to be the only one that thought about bin packing, like, except when you're teaching it in class. And they're all like, what do bins mean here? I was like, bin do you all know what bin packing is?
I don't think so. Is that like the stuff that like
Sure. Okay, just Google bin packing problem sometime. This is part of your homework, okay? Wait, is it? Maybe it's an algorithms problem? It's used in FPGA semiconductor chip design and it's NP hard. Do you know what those words mean?
Yeah.
Okay, all right. Read this page quickly sometime, okay? It's part of your homework. Okay, all right. Some of you know that I'm a linked list apologist. Do I recognize the legitimacy of any data structures other than the binary tree, the linked list, and the hash map? Absolutely not. There are no... If you come at me and you're like, hey, I'm a skip list, I'm going to say, no, you aren't. Okay, so the linked list is an important design pattern to teach, even though its haters will say, hey, you should just use arrays for everything, which is not wrong. You can structure a bootloader as a linked list. Right? Easy, then it can be arbitrarily long, no matter what. So by convention, there's a 512-byte first stage. And what that first stage does is it links to the second stage. What is the second stage? It doesn't matter. It exists in memory somewhere else. By that time, you're out of the bootloader. You can do whatever you want. You can start thinking of yourself as the operating system. Okay. So, the bootloader lives in a reserved physical or logical location. Again, I don't know how this works with solid-state drives, and I don't care. It doesn't seem that interesting. What I think actually happens is there's probably some actually discrete physical memory inside the solid-state drive that's like not the same speed as the other memory, and there's a very tiny amount of it. It might even be firmware. Okay, so the bootloader lives at a specific location, and this is the location I physically always think of as memory location 0. But in point of fact, it doesn't really make sense to think of it as memory location 0, because really, memory location 0 is wherever the OS says memory location 0 is, and the OS is probably not talking about the bootloader all the time. And this is sort of one of the importances between physical and virtual memory. Now, you all are aware of what virtual memory means because you just wrote a memory allocator where you passed back relative addresses that were not relative to anything physical at all. They were just offsets. So we're doing everything in terms of offsets. So we have to somehow find out where the operating system is living. When we say operating system, we're actually going to refer to a specific part of the operating system, and this is the term that we are introducing today. We are referring to the kernel. But here I'm not going to say kernel. I'm going to say kernel image, and I'm going to say that for a reason. So the kernel describes the minimum components of the operating system necessary for software to interact with hardware. So the absolute minimal components. That it's only the hardware-software interface. Why do I call it the kernel image? Because the information that describes how a computer can have its hardware and software interact is simply information, And that information can exist in multiple locations. It can exist on a hard disk drive, and it can also be copied into the DRAM that you made in your job in Boise at Micron using Python and the other thing I taught you, Linux, right? You all know Linux. Wait, I'm making you learn Linux this term too. Oh, that's so cool. I'm such a good teacher. Okay. I think it's unfair that I don't get to take my classes, right? But I guess I could come on Fridays and heckle Jimmy.
You said you were going to do that, and I haven't seen you do that.
So we have faculty meetings literally actually at the same time. So
A likely story.
I can show you my calendar. No, I can't. I'm probably not allowed to show you that. Okay. Okay. So at the kernel, there's a lot of discussion about kernels, and everyone cares about like microkernels and monolithic kernels and all that stuff. I could teach you that in an operating systems class, or I could teach you to write in an operating system. So it's the minimal OS internal. It's the first thing that runs and it interfaces with the hardware. So we're going to imagine here that we have some physical bits that describe this information. And those physical bits start in your storage medium, and then the motherboard, or the MMU, or the bus, or the CPU, they all get together and they copy those bits into random access memory so you can read them much more quickly. And then actually after that they get copied out of random access memory to instruction cache and so on. So they get copied to a lot of different memory locations, and that's what I refer to the kernel image. Your OS is probably not a 16-bit operating system, even though it would be really cool if it were. And so I read this and I was like, I should make them write a 16-bit operating system. And I'm not going to do that, okay? But I want you to know I thought about it. Remember when I made you all implement 16-bit floats? Remember how fun that was?
It was bad.
I had fun with that. It was totally fine. Okay. So instead of using 16-bit mode, one of the things you're going to do as you transition from coming out of boot and coming into sort of a stable configuration where the OS is running, is you're going to transition from 16-bit mode, which is historically called real mode. And I think it's called real mode because it's like the way the hardware is actually running or something, but it's also differentiated from 8-bit mode. Then there's going to go into a 32-bit mode called protected mode. Historically, I understood that as being called protected mode because a lot of the 32-bit stuff, initially, especially when it first came out, was running at lower privilege levels related to coming in and out of, it was just called PM, protected mode. So there was a mode that the processor would go into that was not able to make certain memory queries, which protected some regions of memory, right? And then 64-bit mode is called long mode because the C type for the 64-bit integer is called the long, except on 16-bit devices where long refers to the 32-bit type. So 64 bits are longs except when they aren't. If you want to get really confused, you can refer to them as long longs. And long longs are 64-bit on 16-bit architecture, and also on 32-bit architecture, and also on 64-bit architecture. But they're twice as long as longs on some of those architectures and not on others. This is why we started just referring to the number of bits. Recall we're writing a 64-bit bare metal. So why are we writing 64-bit bare metal? Because we have to. I mean, it's not that we have to, it's that it's easier. So we will deal with this. And how will we deal with this? We're going to hand wave it. That's how we're going to deal with it. We're going to say, I'm going to make this someone else's problem. So here's an exact quote from the blog. I kind of do want to make you write a bootloader, but I also want you to graduate on time. So with those two things in contention, we're going to use a boot image. I have very low tolerance for this. All of the embedded code I've ever written, you look up in a piece of documentation exactly which hex location you're supposed to write a specific other hex value to in order for something to happen on the device. This is like a cool and rewarding thing to do. I think it is just as reasonable for you to learn it in on-the-job training if you go into the firmware space. I don't find it algorithmically interesting. I don't find it technically interesting. It is technically interesting if you don't have the documentation. Then what you need to be doing is doing some experimentation to determine what bytes to write. But it's just not that interesting.
I have a video people could watch about that if they want.
Yeah. And I think there's lots of videos about this. Like every time you buy a new microcontroller, you're just going to be doing this, basically. Okay. So instead of doing that, we're going to use a boot image. This boot image is sort of the same type of image as the kernel image. We're going to use a Rust crate. I believe it's a Rust crate. And what it's going to do is it's just going to build our Rust bare metal executable the same way we build everything else, and it's just going to put a little hat on it, and that little hat is going to be the bootloader. And we are not going to think about it. I'm referring to this as cheating, and I'm recommending you do it all the time. And without further ado, we're going to move on to the kernel. So why do we think they named it after something that is part of corn?
Because it's like it's like metaphorically, it tracks. It's a little bit of something that contains the basis for everything that comes after it.
Okay. I'll allow it. Thank you.
This is what philosophy gets you.
I'm still not sure about philosophy. I worry sometimes that the philosophers are the ones that got us into this mess, you know?
Yeah.
Right, like if someone wasn't around being like, I wonder if we can make rocks think, maybe we'd all like not have to pay property tax, right?
I would say that that's from the scientific tradition, and there's nothing more. Philosophers are not generally interested in finding anything out or solving problems or making any progress in the last 2,000 years.
Yeah, no, it's like the stuff 2000, like I feel like y'all are still kind of vaguely responsible for science, right? Like I think we would have been too stupid to figure it out without the philosophers. Okay. And in this class, we do the artificial philosophy. Okay, we're going to make a kernel. We're going to make a disk image that prints hello world to the screen when booted. We're not going to do that today. We're going to work on that. And we're going to begin by extending our bare metal executable. Okay, that sounds fun. Does that sound fun? Is everyone having fun yet? Okay. Before we go any further, we have to reintroduce the notion of target triples. Do you all remember what target triples are? Okay. The only one that's kind of squirrely is the ABI. I just have never dealt with ABIs because I've only ever used one of them. So matters a lot when you get it wrong. By the way, I would like to point out that the vendor of my device is Intel, which is the largest employer in the state of Oregon. Here, we'll just type in Beaverton here. Do you all do this?
Search for in Beaverton?
Yeah.
No.
Oh, look, it's a summer-fall co-op. Oh, you could do this. Let's see. You have a working knowledge of C for embedded systems and Python, and you probably know. I think you know these things. I think you can all apply for this. Okay. All right. Okay. I am aware of no existing target triple suitable for this course. The guide I'm following just makes its own, so we're going to make our own too. And this is great because I'm always looking for excuses to annoy you more about JSON. I feel like JSON is just underappreciated as a way to express graphs. So we're going to do a little bit of JSON. We're going to express some combination of easy and weird stuff. Wait, that's a typo. Architecture. This is a big thing to hand wave. Manual memory layouts. I just want you to know there's a lot of content that could have gone in there. We're skipping all of it. I don't think it's interesting. Maybe it's interesting from a performance perspective. We're just going to put this together and then we're going to get on with it. Okay, so how are we going to do this? This is not our target triple. Why is this not our target triple? This is not our target triple because this expects an underlying Linux operating system. And we are not allowed to expect an underlying Linux operating system because we are our operating system. But there's some other things in here we are going to borrow. This is hitting an x86-64 target. That's what we're going to be hitting this term. Since this is mostly going to be in QEMU, if you're on Apple Silicon, you should be fine. I don't think any of us are on... Wait, what do Chromebooks run?
Modified version of Gen 2.
Or hardware. What are they?
They're pretty sure they just use x86.
They just use X. Okay.
Probably not efficient version.
Chromebook.
They might use ARM.
They just underpower their components to make it better glass.
They might use ARM.
Chromebook architecture.
Read the instructions of architecture.
Oh yeah, I see. Yes, everyone's telling me they run Linux. I know. Okay, all right.
It's just shockingly difficult information to find online.
I wonder if they don't want me to know.
I love how Google's so useful still.
Yeah, isn't this great? It's about...
Google AI.
It uses built-in yeah.
Yeah, it uses Intel and AMD chips.
Okay, cool. Wait, where's AMD based? AMD, Advanced Micro Devices, right? Who wants to live in Santa Clara, California? Okay, Santa Clara's nice? Okay. Okay, well, let's, Santa Clara. Now, this one's in Cupertino. So I hear Apple's in Cupertino. Gross, right? These are all in Cupertino. Oh, Sunnyvale. Oh, so what you're saying is there's a lot of jobs?
So it should be easy to get them.
That's not what I said. I just said there's a lot of them. There's probably more of them than there are of you. Okay. Do we care about all this? I don't know. We'll go over it. Okay. So most of these fields are required by the Lawrence Livermore Vational Mabulatories, which is what I always think LLVM stands for. It doesn't actually stand for that. It doesn't stand for anything. It's not even based at Lawrence Livermore. Also, I think both Lawrence and Livermore worked in the Manhattan Project. Anyways, the data layout field defines the size of the integer, float, and pointer types. So, I don't know. That looks like an I-64, right? That looks like an I-128. I don't really know what a P32, P7, I don't know. I don't really care. Okay. Rust uses conditional compilation. I don't really know what that means, but they need to know the target pointer width. I would assume this is just like your bit size, but they call it target pointer width. I guess that's fine, right? You've heard me go on pretty lengthy rants about how weird it is that a modern language uses a 32-bit integer. It should obviously just use a 16-bit integer for backwards compatibility with devices in the 80s, right?
This is a strange ongoing bet, the 16-bit truth here. I'm not sure how I feel about this one.
You know, it's a square number, and 8 and 32 aren't. 64 might be a square, but we don't know because we can't calculate values that high.
No, like, not that high. That's
Okay.
how you do computers.
Yeah. So you all heard Linus Torvalds made the I can't count higher than 20 because I ran out of fingers and toes joke again today. That's pretty good. We like to see that. Okay. So next version of Linux is 7, right? 7 fewer than 20. Okay. Pre-link args field specifies arguments passed to the linker. You all have dealt with the linker, right? Remember -t link args equal. Okay. So you've all dealt with that. We're also targeting x86-64 because Apple sucks. We hate them. All right, can I get an Apple sucks from everyone? 3, 2, 1.
Apple sucks.
I feel like none of the people with apples said it. It's kind of weird. Our friends that have apples are still cool though, right? Ooh, that was oddly silent. Okay. Okay. We don't need to dwell on this. Everyone is valid and respected in this class, right? Okay. So, we're going to start with this. And what is this? This is, I yanked a bunch of stuff out of here. I changed the OS to none. Okay. So we'll go ahead and do a grabberino on this. Are we going to do that? No, we're not. Do I want to manually edit this? Okay. I have too many windows open. Okay. All right. So I'm gonna make something called x86_64 because that's my target architecture. And then I could specify a bunch of other stuff, but I'm just gonna say this is for Osiris. Call that JSON, and we'll bring this over. Paste. There you go. Very good. I'll go ahead and write that. See, is there any things we care about here? So I changed this name to none because it's not relying on Linux. Oh no, I'm really getting a bit of a cough. And the other place I had Linux is right here, so I changed that to OS none. I'm going to add some additional arguments. Okay, so when I add something to JSON, kind of actually weirds me out that you're not required to have terminating commas on this, right? So I have to add a new terminating comma. I go to the next line. And then we're going to have our linker flavor. Our linker flavor is, this is kind of cool, actually. ld.lld. So Rust, I guess Cargo. Is it Cargo or Rust C? One of them comes with some kind of built-in linker that you can use if your emergency backup linker isn't available, and your emergency backup linker is usually part of your operating system. So we're going to use the built-in Rust one. And we need to specify both its flavor and its name. So we're going to use Rust LLD. I don't know about Rust LLD. I actually found out about it for this lab, and I think that's kind of cool. You can learn more about it here. Oh, I guess that does not seem like that belongs to Rust. That seems like that belongs to LLVM.
I mean, Rust LLD is based on LLVM, so linker, so.
Yeah, but
It's just slightly modified to work with Rust orphans, I think.
the relevance of this is, I think we should have some discipline about differentiating things that are developed by the Rust people and things that are developed by the LLVM people.
The Rust is one.
Okay, whatever. Okay. So who loves to panic? Right? I am always panicked. Big Rust is always trying to get me to unwind. I never unwind because I like to panic. So instead of unwinding, I abort. I just stop whatever I'm doing and freeze. Sometimes I form an infinite loop and sometimes I crash. Those are great things to do. I've only panicked and given up. That's true. That's all I do. Okay. Fun fact, setting panic strategy abort here means I no longer have to set the panics as abort in cargo toml. Is that true? Wait, no, I hit a button and I don't know what it was. Okay. So, well, okay, I'm gonna do something spicy here. We're gonna go to cargo toml. Oh, why did it default to lock? Because L comes before T? So when I was in kindergarten and they threatened to hold me back because I refused to learn the order of the alphabet, I did not think I would use it all the time in my daily life growing up. But like, autocomplete is in alphabetical order, so I am constantly thinking about the alphabet. And then I went to my physical therapist. That's not true. I still haven't seen my physical therapist. I went to a doctor, not a doctor. Okay, I went to a physician's assistant. There we go. First try. And that person told me to do ankle alphabet. So I have to know the alphabet in order and move my ankle in that way as part of my prescription to like be able to walk. So I use the alphabet all the time. And so if I'm ever teaching you anything in this class that you think you won't learn later, that might be true. Okay. So I'm gonna get rid of these ones because I'm a bit of a hater. Yeah, there you go. Okay. This is slightly better, I think. This is my theory. It was hard to test this. I don't know if this is true. In a little bit, we're going to recompile core. And I don't know if something I specify in cargo toml is going to apply to recompilations for things outside of that crate. So this also hits that crate, I guess. And what is core? All these things have the same name. So standard and core, I like sort of perceive those two words the same way. But what core is going to be is core is basically going to be all this stuff, where it's going to be how to have different intrinsics for different data types and so on. So we're going to need core a little bit, and I can show you exactly one place we're going to need core. We're going to need core in sorc main because we have core right here. Okay? Or I don't know why I did it that way. We have core right here. Never use your mouse. Okay.
Yeah, you should disable it. In bit.
Yeah, I actually thought it was disabled, and then I just used it.
Is it disabled? There's like different levels of what it can do.
Yeah.
What mode it can be used in.
I think I should just turn it off at hardware level. I'm not going to do that right now. Okay. What you should really do is you should have a desktop and not have a mouse plugged in. Like, we all understand that's the natural state of computers, right? And also, I don't know if any of you all tried this, but I successfully used, I think during my summer internship at Seagate, I used Windows without a mouse that entire summer. Everyone thought that was really cool. They didn't think I was annoying at all. Or at least none of them said to my face they found that annoying. Okay. Okay. All right, folks, it is very painful for me to hand wave this part. Disable red zone. The red zone is awesome. And what is this? This is a Boolean, so it is not enclosed within quotes. I accidentally... See, I started using the mouse, and now I don't know what I did with it. Okay, so the red zone is awesome. Okay, red zone, awesome. How's the red zone awesome? Okay, so you are a computer. You know at this point in time that running, I don't know, yeah, the executables while being executed, they have both a stack and a heap, right? You're working with both of them. On the stack, you have a bunch of things of known size, right? So that's your working memory. You're keeping your integers there. You're keeping other stuff there, right? Okay, so on x86, 64, and actually, I believe on 32, actually, there's this thing called the red zone, and it's awesome. Because usually when you have a stack, you can only do push-pop operations on them, right? And in fact, that's why there was a stack, and all of computing was organized around having used the stack as a stack for a gazillion years. And in order to use the stack as a stack, the way this worked is inside your computer, there's one register, and it stores the address of the top of the stack. That's called the stack pointer, and it's 64-bit. It's the RSP because 64-bit registers are R prefixed. That, I have never seen this before. Are you all looking at this?
That's so weird.
Am I losing my mind?
That's very strange.
It didn't do it that time? Okay, I'm stun locked. Okay, so you got a stack pointer. Stores the memory location at the top of the stack. Do you care where the bottom of the stack is? No, of course not. You're just going to push and pop off of it. You know how big it is. Okay. Those brain geniuses over at Intel, and actually probably more the compiler people, were like, what if we just put stuff on the stack and don't update the stack pointer? We're just gonna start throwing stuff on the stack, right? Because every time you update the stack pointer, that costs you one instruction. Which means that if you're just like saving a bunch of variables or pushing a bunch of things, like, you have to change the stack pointer a whole bunch, right? So they're like, yeah, some functions just don't have to actually maintain the stack pointer. And instead of pushing or popping off of the stack, they can do load and store operations like load word and store word and URL setter and getter for malloc. They can just do that with negative relative indices compared to the stack. So you can write things off the end of the stack and then still access them via like random access, right? This only gives you a little bit of space, but you should only need a little bit of this anyways. Here is an example of a sequence of assembly instructions that gets higher performance with this. So we imagine we want to, I don't know.
I'm going to go over something, but then you just really love the red zone so much.
I got stun locked by the red zone. The red zone's insanely cool. Okay. I'm not going to go over assembly. That's true. Okay. The red zone allows you to use a stack as an array. And arrays are better than stacks. Okay. If you're like looking for something to do with your life, go through these. They're very cool. You all know that I hate floats, and with good reason. BlogOS asked us to add this. Wait, I didn't even know I said "and with good reason" on these slides. I just instinctively say "and with good reason" every time I say I hate floats. Okay, so we're going to add one other thing in here, which is we're going to add some features. Okay, folks. These are not the machine learning features. The term feature is used for everything in computer science, okay? These, I would not call them features at all. These are ISA extensions. They're extensions to the instruction set architecture. They have nothing to do with features at all. It's crazy they're called features. These should be called extensions bare minimum. Okay, and what are we going to get rid of? We're going to add a minus in front of some, then we're going to do MMX, SSE. I don't remember which ones these are. I think of these all as part of like VAX, which is the vector instructions. And we're going to add soft float. And I have slides that are going to describe what these do. But what is this? One more. MMX and SSE are pretty, these things are historically interesting. It became clear at some point in like the late 90s and early aughts that CPUs weren't going to be fast enough if they worked with one piece of data at a time. This ultimately led to the current explosion of GPU influence. But there was this intermediate time where everyone was still running all their code on CPUs because they didn't realize they could use GPUs for anything yet. And so the CPU manufacturers came up with these SIMD instructions, which is single instruction, multiple data, right? SIMD? Yes. And so I just call these things vector ops because essentially what you're doing is you do an operation to a vector of values instead of a specific value. It's the basis of NumPy, it's the basis of other things. But at some point in time, so I guess these ones came out in 97. I think of it as Intel, and presumably AMD was doing the same thing. I sort of only get the side of the story from Intel because I've only worked with them. They started just jam-packing their architecture full of all these SIMD instructions, trying to get higher and higher performance. And MMX and SSE were, I guess, two of the first ones that came in. And I think the big one is VAX. This is the big one. But so we put all those together. And SIMD instructions matter a lot. Should I make you repeat SIMD after me? Repeat after me. SIMD matters a lot.
SIMD matters a lot.
Okay. And so this was where all CPU performance was coming in for a few years before NVIDIA took over. We're turning these off because we don't frequently do vector instructions inside an OS. And there's things that cause them to be expensive, and we're turning them off to get higher performance. Now, on x86-64, and I didn't know this, internally the float optimization or the float operations are optimized to use SIMD instructions. That kind of makes sense to me. I can see why you do that. So in order to turn off the SIMD instructions, we also have to turn off the floats. This is just two good things, right? I want my computer to do less and be worse and be slower. So this is really great. But, and I didn't know this, Rust core is like jam-packed full of places that use floats, it looks like. So you still have to have the ability to use floats without using hardware floats. You all know the solution to this because I made you write your own float library. You implement floats in software, folks. So instead of having hard floats, we have soft floats. Rust includes an ability to use software floats, and so we're going to turn that on so we don't use the SIMD registers. It is, to me, admittedly weird to turn off vector instructions to get higher performance and then turn off floats to get worse performance. So we're going to loop back to this later. But you, as students, are already aware that you can write software floats. And then when you have implemented, you've hit the target feature, so the hardware version of the software float, which is going to impact sort of what instructions are generated. We're also going to have to change the API. So we're going to do x86 soft float. I remain 100% sure I can write an OS without using floats, and I'm going to keep working on that until I succeed. Okay, so I think this is what it looks like. I don't really know, but there's a fun little trick you can use, which is that this is all part of the blog OS, so you can also just curl this if you don't want to type the whole thing. And I know you don't believe me, so I'm going to save that. I'm going to move that to other.json, and then I'm going to do the curl command, and then I'm going to diff them. Presumably that means I spelled something wrong, right? Oh, no, it's the terminating comma. So the only difference is my terminating comma in my last line, right? Okay. So I have my two different JSONs, which are both suitable for my task. Okay, so this is what I have. Looks relatively similar. I just have other up here as well because I saved it. I should let you know that I've switched. Yeah, so I turned off. You'll remember when I had an infinitely recursive main instead of a loop main. And then what happens if you actually successfully load that in QEMU, it instantly segfaults because it keeps creating a new call stack. and the stack takes up memory, and there's a finite amount of memory, so you just consume memory at the fastest possible rate until crashing. No one told me, what did I press? Oh no. Okay. No one told me Rust was bad, so I didn't know that was going to happen. So, it depends. There's a Jimmy quote? Okay. So I'm just going to pop a loop in here, and I'm going to feel bad about it too. So I think that's probably fine. Okay. So this is what I have. I think on panic it doesn't matter because by the time panic it gets called, you're cooked anyways. So I don't think that matters. Okay. We need core to panic abort. I showed you that already. Okay. So we are not going to use Linux, but I think of Linux and C in the same way, where like there's an actual operating system called Linux, and there's like an actual programming language called C, and then separately, throughout human history, the only operating system has been Linux, and the only programming language has been C. So there's all these things that seem like you have to do them in a certain way because there's only one way they've ever been done. One of the examples I give of this is, so I speak English, and in English there's this word religion, and I feel like when I was growing up, people kept trying to come up with religions other than Protestantism and Catholicism. And they're like, oh, like Shinto is a religion. And it's like, not really. That's not the same. You wouldn't use the same word for that. Your language is just completely cooked, right? And so there's so many assumptions about computing and the history of computing that are baked into using C and using Linux. We can't get away from all of them, even if we're not running on top of an underlying Linux architecture. The same way, like, even if you are an Anglophone who is an atheist, you probably still refer to paid days off as holidays, even though that means holy day, and you don't care about that stuff, right? So the English language is totally cooked. Computer science is totally cooked. We're all doomed. Time is a flat circle. Okay, so, having said that, we're going to use Linux calling conventions. And so we're going to use the LLD linker flavor. And with the use of that linker flavor, we're going to need to have a start entry point. I think mine is not called start, so I'm going to call it start. And I bet when I compile this, it'll work. So let's go ahead. Let's go ahead and rip a cargo B. Wait, cargo B sounds conspicuously like Cardi B, does it not? Who I was sure was going to show up at the Super Bowl halftime show, and then didn't. So all of you, this was the first song you heard Bad Bunny in, right? 7 years ago with Cardi B, right? Yeah. You know, we got Lady Gaga instead. That's the wrong person from Brooklyn. Okay. Oh, there's anything wrong with Lady Gaga. Okay. Hey, look, I have a viewer. Which one of you is it? Okay. Okay. Let's see, what went wrong here? Is this the error I'm supposed to have? Oh, no, this is a different error. Okay, so I got this error because I didn't specify what my target was. That's no problem. I can fix that because I'm a genius. So I'm going to come over here and I'm going to cargo B, and I'm going to set my target. I'm going to try and set my target. And I'm going to set it to the JSON file. Boom! Press enter. Okay. What problem do we have here? Ooh, okay, core. We can't find the core that corresponds to this build triple. And that's a little bit unsurprising because this build triple doesn't actually exist. It's just a JSON file. I just made it up right now. So it's not going to have the level of support that actually existing build triples have. So what am I going to do about that? Well, wait, no, I totally skipped something. Did I not? Did I skip something, folks? I thought something wasn't going to work. Well, things are not working in an unexpected order. Anyways, I'm going to go out of order on my slides because I have the correct slides for this. The thing that I got here is I can't find a crate for core. And we all know what core is, which is the 2003 American science fiction disaster film about boring into the center of the Earth to, I think the center of the Earth stops rotating and like the planet's going to get destroyed. Yeah, you remember the core, right?
It's terrible.
But it passes the Bechdel test.
The only thing I've heard of that.
It's still bad.
Okay, So instead of watching the core, what should you watch? What is the Alien film that came out closest to 2003? Alien versus Predator, right? Which also involves boring a hole into the earth and going inside of it. So it's basically the same movie. Also not a good movie. Okay. So that was actually not the core I was supposed to talk about. I was supposed to talk about the Rust compiler core library. It contains result, option, iterators, and some other stuff. And it is used in no standard, which we have. Do you all remember having no standards? Sorry, I can stop anytime I want. See, look, I have no standards. Okay, so core is precompiled and then shipped as, no, they're going to say a binary. It's just shipped as a library. It's a linkable library. We made a new target. It needs a new core. So we're going to tell Rust C to compile for that new core. No problem. How are we going to do that? I don't know a graceful way to do this, but this way isn't super ungraceful, so I'm going to do the not super ungraceful way. Okay, are you all ready to be not super ungraceful? Okay. I'm going to create a new file in the hidden cargo directory called config.toml. Okay? So we've seen toml before. Let's take a look at our, what am I doing? Let's look at some toml. This is what toml looks like. It stands for totally oblivious minimal language, or something like that. And so I'm going to make my new directory, which is the hidden cargo directory. I can't see it, but if I list everything, I can see the hidden directory. And if I do a, oh gosh, I built something. There's cargo, right there. You'll notice I don't have a hidden git, but you might, or something like that. Okay, so I made my hidden cargo, and then I'm going to open cargo config.toml. Okay, and so I'm going to use this file as a way to sort of pass ideas to cargo about things I want it to do that are hard to pass at the command line. And so the first one I'm going to do is I'm going to pass the idea that I want to build standard. Okay, so check it. Oh, check in. Oh, there's check in. Okay, are you all ready to check in? What would have happened if I didn't make cargo before I tried to open .cargo/config.toml?
You didn't make .cargo.
Yeah.
There would be an error because the directory doesn't exist.
Yeah. So maybe this is only like Calvin's Vim or something, but here we can demo.
Doesn't Vim make the thing for you if it doesn't exist?
It makes the file.
It makes the file, but not the folder.
I would have figured you could configure to do that.
See, that's what I would have thought too.
That's something you can configure.
So it works on mine, but it didn't work on WSL.
It by default lets you edit it, but won't let you create it unless you specify when you're saving that you want it to be created.
Okay, so all right, we are going to use something called the build standard option. So if for example you're going through your life and you have no standards and you want to build up your standards, you can use the build standard option in Cargo, right? We are going to do this so we can recompile core and the other stuff we might need, even if we were past things, past a target triple for which we do not have core. Okay, so we're going to start with a relatively sparse config. And the only thing we're going to do in here is we're going to specify we want the build standard option for core. And I think I missed a single equals assignment. Is that assignment? I guess I'd call that assignment. And so we're going to go ahead and we'll just save and exit that. Wait, what? No such file or directory. Oh, okay, this is where it's stopping me. Okay, so no problem. I don't know. I don't know exactly what you're suggesting, but I support you. Okay. Cargo B. Oh, I need the target triple too. Is that in here somewhere? Wow, I type a lot. Wait, I still got the same error? But it says over here, I bet this will work. I sure hope I didn't bamboozle my... Oh no, that's what the slide said was going to happen. I got the same error as before. Okay, that's not to worry, I have a plan. So, build standard is not a stable feature of the Rust language, which means they might remove it anytime. I don't know if any of you have ever professed a class, but relying on something that might be removed from the language you're using at any time is slightly stressful. But I've gotten over that because I trust all of you now. So we're just going to start using unstable language features. So no problem. We're just going to specify that this thing is unstable. I want to introduce a mental model here on unstable language features. I think it is helpful that we have introduced unsafe already, because I'm going to kind of draw this parallel. And this isn't a parallel I've seen before. I don't know that it's necessarily particularly useful, but I do want to draw it because they both have the un prefix. Okay, so we can create in Rust executables which we permit to do things that are potentially unsafe. We don't necessarily know that they are unsafe, but certainly we can intentionally write something that is unsafe. And when an executable is unsafe, what does that mean? It means when I run the executable, it might do something that a safe executable cannot do. And one of the things a safe executable from Rust cannot do is it cannot have a runtime crash unless you intentionally put some panics in it or something, right? But it can also do sort of things you just don't expect the executable to do. And the example I always do is leak your private key, and then the other one is always you say delete the production database, right? So when you start running executable code on your device and you don't really know exactly how consistent it is or how it's going to work, you never know what's going to actually happen to your physical device or to its internal memory or its internal state or anything like that. Okay, so that's unsafe executables. But what does it mean for a language to be unstable? Well, it might mean you have some source code that at some point in time is reasonable. It does not leak your private key. It does not delete the production database. It does not crash, right? And you compile it one day, and then you go to sleep, and you wake up the next day, and then you compile your code again, and now it deletes the production database. And why did it change? Because the language changed overnight, because you were using unstable language features. So even though your code is unaltered, the resultant executable changes. That's what it means to have an unstable language feature. Now, the portions of the language we're going to fiddle with are not necessarily in... I don't know if you want to think of this cargo toml or this config toml as like part of the source code. It kind of is, right? So we're going to change the way we compile our code in a way that might not work tomorrow. So we're going to prefix this with an unstable. That's not what I meant to do. Okay. Unstable. And now I bet it'll work. Okay. Oh no. It still didn't work? Wait, no, it said it's okay. I bet it will work, but it won't. Okay, so I bet this is fine. Okay. The exact same error as before. Folks, I feel like I'm not fixing the errors at all. I hope you're enjoying this process. Okay. So this is exactly what I was hoping to avoid all term, which is we're going to use Rust nightly. And did I want to use Rust nightly? No, I'm using Rust nightly with a heavy heart. We need build standard, which means we need unstable. And to use unstable, we have to use the unstable version of the language. And the unstable version of the language is the nightly version of the language. So we're going to use Rust nightly, okay? We're not going to overthink it. We're not going to admit that people that suggested we should use nightly the whole time were correct, okay? We're not going to do either of those things. The only thing we're going to do is we're going to type plus nightly in between cargo and any of our other commands. Okay? So I'm going to go ahead and do that now, and I bet it's going to be totally fine. Okay? Wait. Oh, I'm not in the wrong window. Okay. So this is my current command. Plus nightly. Oh no, I have to get nightly. So I think this takes like a million years. How long does this take?
Not that long.
Not going to take that long.
It'll take a second. But
Let's play the Wordle while it goes. Okay.
what if I already did the word?
It's spoiled.
Okay, we can't spoil it. Can we do the LA Times Mini?
Do this semantic. Or it's horrible.
Oh, the LA Times. Okay, yes.
It's horrible.
Which one?
LA Times did it this morning.
Lily Pad Traveler, frog. Have a yen for?
It's working now.
It's,
No, now we're doing the mini.
Okay.
White House staffers. Tango teams. Is this pairs? Typical introduction.
Hello.
I'm willing to do hello, but okay. Friar. We got cooked.
Greek.
I just tried to use vimd right there. Okay. Wait. Where are we? The R radio? No.
National Public Radio.
Okay, what's this one? Hardly Secret. Painter's Base Layer. Grout.
I think 3 down is overt. You think? Yeah. What's it again?
Wait, how over? I can't do things. Do we? Okay, what's this one? AIDS.
AIDS, yeah.
Crave.
Have a yen before? Guess so. Guess so. It's an O in the bottom right.
That's an O.
Yeah, that's a word.
Typical introduction.
Grotto. What? That's always what I say. I say, hey, grotto.
Is it
What is that?
Proto?
Yeah.
Yeah, prototype for prototypical introduction. Huge.
That sucks. That sucks bad. Except for proto, I think we're fine.
No, it's turbo cringe.
I mean, it's an art thing. Yeah, so.
Yeah, well, it should have said, what's nothing.
Oh, so, I mean, I think if the AI overview knows about it, we should know about it.
Why? I know about it. I can tell you exactly what
It's not in my training password.
Okay. All right. Well, it's good that now our cargo build worked, and there's no errors, right? Here, I'll demonstrate again that there were no errors. Wait, there's still an error? Folks, there's still an error. What should we do? Well, this error just like says what you should do. So we'll demo and straight that. JSON target spec. Rust up component add Rust sork tool chain.
Do this in a Rust file.
I was specifically not doing that this week, but yeah, you can teach them that on Friday if Jimmy's busy. Do you want to teach them that right now?
You use the .cargo configuration file to like make.
I was adding one a day. That's why I don't know.
I don't know.
Yeah. Did that work?
Use roll under roll.
Now it'll work. Wait, it's working?
I mean, it's gonna probably get to what it's compiling your thing and then fail.
I think my crate's awesome.
Good inset.
That took 14 seconds. Yeah, no, so this works now. Okay. So this is how you fix this. Okay, so see this? That's annoying. And okay, I'm going to tell you why I'm getting irregular behavior between my two different my slides and the other thing. Little cat. These are integers. There's a version of Rust C that requires them to be strings. I have that version on my home device, but not on this device. That's why I'm getting different behavior. And the reason for that is it was fixed in like, I don't know, at some point in time. It is fixed in nightly. I didn't think it was fixed in stable. Apparently it's fixed in stable. I don't know. So if you're going through the slides later, there's going to be references to changing these back and forth. Now, I am slightly annoyed that it isn't broken here, because I think like one of the most useful things I can teach you is how to deal with these sort of annoying side bugs that don't really matter. And I literally found the GitHub issue where they fixed this and changed it. So that was going to be what I was hoping to be a good example of a difference between the stable and unstable languages, where this is an improvement in the stable language, but it's kind of weird. So anyways, that's the two differences. We successfully built. We come back on Wednesday. After building it, we're going to run it. Or I think the lab is called boot, because we're going to boot.